So, the more interesting things that they showed here was that right, this is actually is good. I mean, obviously since this is essentially estimating the gradient, right. So, if you follow this gradient estimates, you will converge to local optima, right. There is nothing really to show there, right. This is the exact estimate of the gradient, no approximations done, right. So, as long as you have a way of doing this, is all great. But then we know that there is no way that you get q pi directly, right, and there is always some kind of an approximation associated with pi, right. So, now what happens is if I can't estimate q pi, right, and if I am going to approximate q pi, let us say I have another function approximator, right. So, I have pi that is parameterized by theta, let us say I have q that is parameterized by some other set of things, let us call them w, right. I have some parameters w that represent the q function, some parameters theta that represents the policy, right. Now, when can I guarantee some kind of convergence? Right. So, here is an interesting result. Let us assume that fws comma a is some q hat, right. So, some q hat of, so it is an approximation, right. So, I am going to denote that by fw, okay, and I am going to look at the error, right. So, let us say I look at the squared error between the true q function, which I do not really know, but let us assume I am just looking at it for showing some steady state results, right. So, I will say that have the q function, right, and this is the prediction I am making, I am looking at the squared error, right. So, if I am going to make changes to my weights, right, so as to minimize the squared errors, so what will be my changes be proportional to? The gradient, right, gradient of this function, right. So, what will be the gradient of this function? Gradient. So, basically I am looking at the dou by dou w of the error, right. So, dou by dou w of the error will be, I can lose the 2, that into dou f w right, dou by dou w of f w, right, and I have to go in the opposite direction of the gradient, right, that is a change. So, my minus will go away, right. This is clear. So, this will be the change I will make to a weight, correct. Okay. So, how often will am I likely to make this change? As often as I pick the SA, right, as often as I pick SA. So, how often will I pick SA? Well, that is one part of it, right, and then I have to be in S, right. If I have been running pi for a long time, what is the probability that I will be in S, right, and so what will be the total changes I am making to the weight function? Right, this will be the total change I am making to the weight function, right. So, if the total changes I make to the weight function goes to 0, then converged, right. So, let us assume that has happened, let us assume that my value function has converged. Okay. So, now we have a theorem that says that this looks remarkably similar to the theorem that we had earlier, right. There in the absence of any approximation on the value function, right, we wrote this saying that dou rho by dou theta is this quantity, right. So, when I am doing function approximation and if the function approximation has converged to some local point, right, so that the weight changes are 0, and if my the parameterization I have chosen for FW is consistent, this condition is called the consistency condition, is consistent with respect to the parameterization chosen for pi, okay, and the way they define consistent is like this, right, dou f by dou w is equal to dou pi by dou theta into 1 by pi sa, right, it is basically dou ln pi by dou theta, right. If the value function here, right, if the gradient of the value function is equal to the gradient of ln pi, right, then I get a very similar condition, but with my approximate function put in, right. So, essentially what it tells you is in a rough way, what it really tells you is that you really only need to get your, in some sense, your relative ordering correct. My FW can be very wrong, right. So, what does this convergence condition tell you here? Okay, let's do a special case, then it becomes a little clearer. Let us take our favorite softmax, right. So, theta transpose phi SA divided by summation over B e power theta transpose phi SB, right. So, this is like the softmax kind of a value function, okay. So, what phi SA is phi of S comma A, like I wrote there, okay, I just made it shorter for me to write. It is some phi vector that represents the state action pair SA, Well, yeah, so I know it's a little, suddenly I switched back to being more mathematical than usual, but I hope people are coping, right, that is fine, okay, good. Now what does this condition mean? I really need my so what should that be? All of you know how to take the derivative of softmax, come on.
What does consistency equation mean? And that's an equality.
That one, right? So if you put this back in here, right, so what does this mean? So this essentially you will get dou pi by dou theta into 1 by pi sa. So 1 by pi sa, 1 by pi sa will get cancelled, right. So you will essentially get dou pi sa by dou theta, right. So what it essentially tells you is in the direction in which the policy is varying, right. So the error is 0, that is what the equal to 0 part is. So you are looking at the direction in which the policy parameterization is pushing you, dou pi by dou theta you are taking that, and you are projecting the error q pi minus fw on that direction, right, and that what you are getting summed over all s is 0. Essentially it shows that my value function approximation is sufficient to represent any variations I would have in this policy, right. If I increase the value of an action in little bit more, like the probability of picking an action a little bit more, right. So the error that I have in approximating the value function in that direction is essentially 0. So that orthogonality is whatever is what you are looking for from the value function approximation. So you should, if your policy parameterization is very weak, right, then consequently your value function approximation also can be pretty weak, in the sense that you do not really have to make too many fine distinctions, because there are only a few directions in which you can change your policy, right. But if your value function policy parameterization is very rich and you can represent all possible policies, then your value function approximation also will have to be equally nuanced. So that is essentially what that condition means, right. So people see that, right. If you take this expression which is dou f by dou w, substitute that here, that you will get a dou pi by dou theta and 1 by pi sa, 1 by pi sa will get cancelled with this pi sa. So all you will be left out with this error term, right, q pi minus fw into gradient of pi sa by, I mean dou pi by dou theta, right, that is the gradient of pi sa. So in the direction of the gradient, right, this error should be 0. So when you project this error in the direction of the gradient, you should get a 0. So that is essentially what you are, or the expected value of the error in the direction of the gradient, expectation taken with respect to d pi s should be 0. So that is the consistency condition, right. And yeah, there are a lot of theories about what will satisfy this, and one thing which I will show now, I will give you one example of what will satisfy this if somebody will actually give me the derivative. Well, I have it here, but somebody will give me the derivative, that will be good. Okay, in the interest of time, it tells me nobody did the reinforce homework.
We did.
I forgot all about it. This is exactly what I asked to do in the reinforce homework, right. Find the updates for the softmax. Right. So that is that. So what is one easy way of achieving this? What's the easiest way of achieving this? Make it linear in those. right? If I want the gradient of f with respect to w to be that quantity, then make it linear in that quantity, right? So w transpose that. Now I take the gradient, it will give me that. Very simple way of doing it. In fact, Tsitsiklis has hypothesized that this is the only way of doing it. Okay, so in general, it's going to be hard to do anything else other than coming up with a linear combination of the, what are fees? The representation I am using for the policies, right? Phi is the representation I am using for the policy, and so the representation I am using for the value is essentially some combination of fees, right? Some linear combination of the fees. So phi SA minus that. So for this is fine. So people agree with this. This is clear, right? Okay. So now let's look at another thing. So for a given state, what will be the mean of the feature vector? Yeah, so essentially summation over A. Right, the mean, that's the mean of the feature vector. What will this be? So something else I need to do. Okay. Yeah. So I need to know how often I will be taking action A. Yeah. 0. Right. So essentially it will be pi A to SA, and that will go away because there's only B terms. I will take it out. So pi SA will become 1 there. So it will be summation over A pi SA phi SA minus summation over B pi SB phi SB, which will be 0. Right, this 1 by A will not matter at all, right. So this will be 0. So essentially what is happening here is I have taken the same parameterization, same features that I use for the policy, made it 0 mean in some sense with respect to the pi SA probabilities, because that is a probability of me taking an action, right. So made it 0 mean for each state, and that is the parameterization I am using for the value function. Okay. So that is essentially the relationship that you would need between the policy and the value parameterizations. Okay. So what does this guarantee? It guarantees that I can just plug in the approximate value function for the actual value function in that expression, and I can still estimate my gradient. So where is that expression? Right. So instead of the Q function I plugged in FW. So FW is a sufficient enough approximation because in the direction I am going to make any changes, right. That is what we are interested, right, because this is the direction in which I am going to make changes. In the direction I am going to make changes, the error between Q and F is 0. That is essentially what we got here, right. If you substitute this consistency condition here, you will get that in the direction of the changes, which is this guy, the expected error will be 0. So that is essentially what you are getting here. It is a very simple thing in hindsight, but it was a very powerful result when they initially showed it, because it showed that you could actually use value function approximation, right, under the consistency conditions, and you are guaranteed convergence, right. So that is a very powerful result. Okay, this was the first such results for any kind of reinforcement learning algorithm where they showed convergence with arbitrary parameterization. The only thing they require is the parameterization you use should be not linear, then it is not arbitrary, right. So well, okay, you could say arbitrary linear parameterization, no, arbitrary differentiable parameterization. So this just assume that you have the gradient that exists, right. So they didn't assume that, right. So the thing is, Tsitsiklis surmises that this consistency condition can be satisfied only if you are going to do something linear, right. For completely non-linear parameterizations it might not be satisfied, but we do not know for sure, right. It could very well be that there are actor-critic architectures where this is satisfied, and then you get convergence, but that is a very powerful result, right. So good. So any questions on this? Then we will stop. 0 by 7.